So in today's lesson, we want to start proving some trigonometric identities. So these are some things that you know so far about identities in trigonometry. We know that Pythagorean identity, sine squared plus cos squared equals 1. We also know that we can express tangent, cotangent, secant, and cosecant in terms of sines and cosines. So everything always comes back to sine and cosine. Well, there's two others that we want to talk about for a little bit. The first one is that the square of tangent plus 1 equals the square of secant. And also that cotan squared plus 1 equals cosecant squared. And what I'd like to do to show you about like proving some identities is not draw a line like that goes across the page, but instead, let's take a look at how we would prove that one of these is true. So here's how we can get this other identity. What I'm going to do with this Pythagorean identity that I know so well, this sine squared x plus cos squared x equals 1. What I want to do is I want to divide everything by the cosine of x. And look what happens when we do. If I divide this by the cosine of x, this one by, cosine squared of x, I should say. Divided by cosine squared x. Otherwise, nothing happens. When I take that original Pythagorean identity and divide everything by the square of cosine, I get sine squared over cosine squared. As we just saw before, sine over cosine is tangent. So sine squared over cosine squared simplifies to tangent squared. In the middle one, the same thing's on top and bottom, so that just reduces to 1. And on the right side, I have 1 over cosine squared. That's the reciprocal function for cosine, and that's secant squared. In a similar way, you can verify the other identity by dividing everything by sine and seeing how that simplifies. So we have a couple ground rules real quick as we go through these identities. Here's some tips to it. First of all, practice it. Okay, the more of these you do, the more trends you start to see, the more things you're aware of that you can do, and the easier your problems become. Ideally, you only want to work on one side of the identity. The idea is that the identity is an equation. Start on one side and turn it into the other side using your knowledge of trigonometry and some algebra skills. Sometimes it's helpful to express things in terms of sines and cosines. That's typically a good thing because, as you saw, sine and cosine can represent all the other trig functions. And at the end, you want to write like a little concluding statement, like LHS for left-hand side equals right side. And notice that I use like a triple equal sign. So that triple equal sign means the left-hand side can be shown to be equivalent to the right-hand side. Or simply write QED. QED is Latin, I think it's for like, something like that, which means I'm done. Or I've demonstrated what I need to show. So let's start off with one. Let's prove that if you have some value for x, and you plug it in, that the tangent of that value plus the cotangent of that value is going to equal the cosecant of the value times the secant of the value. Please note that there is an implied multiplication right there. So the rule is we got to work one side only. I'm going to start working on the left side, and I'll talk to you about the end about working on the right side. So I see tangent plus cotangent. One of the things I'm thinking about right away is let me get them in terms of sine and cosine. So I know tangent is sine x over cosine x. And cotangent I can write as cosine x over sine x. And I'm going to keep doing that equal sign because the equal sign shows me, it demonstrates that my left side is still equal to my right side. Now, you might remember that if we have some fractions, we can kind of add them together. So my common denominator here is going to be the product of cosine x and sine x. So I'm going to have to, in order to change the left side, I'm going to have to multiply it by sine x on top and bottom. And I'm going to have to multiply the right side of it by cos x, top and bottom. So what that's going to give me is sine x times sine x, which is sine squared x. And if I multiply the cosines together, I'm going to get cosine squared x. When I combine them with a common denominator, my common denominator is sine x cosine x. Now, here's a good reason why we want to get things in terms of sines and cosines. Because we know that this identity it's an identity in the numerator. Sine squared plus cosine squared, that equals 1. So this whole thing reduces to 1 over sine x cosine x. So this is pretty good. We're getting somewhere. We got rid of our two big fractions. Now we're down to just one fraction. And what you can do with this fraction here, because the denominator is two things being multiplied together, we can separate it into two separate fractions. So I'm going to rewrite this as 1 over sine x times 1 over cosine x. Just like we can multiply two fractions together to get 1, we can pull 1 apart to make 2. And you might see that this is looking pretty good now, because 1 over sine, the reciprocal of sine, is the cosecant of x. And the reciprocal of cosine is secant of x. And the way I like to finish it up is I've shown that the left side can be expressed as the right side. So I'm going to rewrite it here. Cosecant x, secant x. Maybe we do like a QED to show that we're done. I'll put a happy face because I'm happy now. Here's another one to take a look at. Boy, oh boy, they look like really, really similar to each other. Just like reciprocals, change a sign somewhere. Now remember the rule though, you can only work on one side. So I don't want you to go like cross multiplying or anything like that. Don't do any of that stuff. But here's a little tip for you. If you see something like a 1 plus cos x or a 1 plus sine x, what you can do is multiply it by its conjugate. Do you remember from Algebra 2 what a conjugate is? All right, let me show you what a conjugate is. Conjugates with polynomials are things like x plus 3 and x minus 3. Conjugates in irrational numbers are things like 3 plus radical 5 and 3 minus radical 5. With imaginary numbers, things like 4 minus 2i and 4 plus 2i, those are conjugates. Conjugates have the same numbers, same terms, but they differ by their sign. So maybe this time I'll start on the right-hand side. And what I'm going to do is I'm going to take that, I'm going to multiply the top and bottom of the equation, top and bottom of the expression, by the conjugate of 1 plus cos x. So I'm going to multiply my denominator by 1 minus cos x. But remember, whatever I do to the top or the bottom, I got to do to the top. So I'm going to multiply the numerator by 1 minus cos x as well. Now, some good things are going to happen. I'm not going to worry too much about the top. But the reason why you like conjugates so much is because when you multiply them together, certain terms cancel out. I'm going to go back to that thing with the complex numbers before. If you have like 4 plus 2i and you multiply it by 4 minus 2i, when you do your distributing and you get like 16 and a minus 2i, oops, that's a minus 8i, sorry, and a positive 8i, those cancel each other out. And 2y times negative 2i is negative 4i squared, which is really positive 4. So when you multiply a conjugate by itself, or when you multiply two conjugates together, you're really simplifying a lot of stuff. And look what this will simplify to. If you're going to do your distributive property, 1 times 1 is 1. When you multiply the outside terms, you get a negative cosine x. When you multiply the inside terms, you get a positive cosine x. When you combine those, they cancel. So now you're left with a positive cos x times a negative cos x, which is 1 minus cosine squared x. And that's pretty cool. I'm going to go back a few pages for a minute. Oh, no, hold on. Let me set this up because I kind of put that in the wrong spot. I want to take this and I just want to move it down a little bit, because that's really the denominator of my fraction. And my numerator is still sine x times 1 minus cosine x. Now let me talk to you about that denominator for a little bit. Let me go back a page or two. One more page. If I take this identity here, what I can do is I can just rewrite this by subtracting cos squared x to the other side. And what it gives me then is that sine squared x equals 1 minus cos squared x. And likewise, I can rearrange the terms to solve it for cos squared equaling 1 minus sine squared. So that's my substitution I'm going to make. I'm going to take this 1 minus cosine squared term, where is it? There it is. And I'm going to replace it with sine squared x. So now my numerator hasn't changed yet. But look what my denominator becomes. 1 minus cos squared is sine squared. And that's pretty cool, because now I can do some canceling. I have a sine x on top, and I have a sine squared x on the bottom. So the sine x on top is going to cancel one of the two sine squared x's on the bottom. So what I'm going to get then is 1 minus cos x over sine x. And I think that's what I wanted. Yes, it is. Woohoo! So we bring that down then. 1 minus cos x over sine x. So I've got my left-hand side equivalent to my right-hand side. And I'm going to write AOG because all is good.